whether they both get arthritis. And one of the things which I'm using human pose estimation for is actually detecting joint movements to then determine whether or not there's rheumatoid arthritis in the joints. So what are the ways that we can actually represent the human pose? So the way that I represent the human pose in my research is the kinematic structure. This is just a simple 2D skeleton, or 3D skeleton in my case, because it's simple to understand. It's quick and efficient for computations. It's just a vector of numbers. It's useful for biomechanics, so you can look at joints and limb angles. But sadly, is you get no textural shape information. So we actually don't really know the size of the person or like how their skin might interact with another person's skin. Then there's like a volumetric representation. So this is a detailed 3D representation. It more accurately shows body types, but there's lots of parameters because obviously you're dealing with meshes. So they do work in real time. You can get real time volumetric applications. They're just very GPU intensive. And then lastly, just to throw it in, there are like some very traditional ways to represent a human pose, which is like planar. It's not really used anymore, but just saying that these are the two which are used, but there are other approaches you can use to represent a human pose. So I'll happily say I'm not a theoretician. I'm a practical applications person. So although I like to think that my math skill is very good, my PhD journey did not involve many maths, and I'll show you exactly what I mean in a little bit. But my whole PhD is kind of centered around developing an application that, assuming I have no prior 3D data, I can convert 2D key points obtained from a single image or video into an accurate 3D human skeleton, where these 2D key points were going to be acquired from off-the-shelf detectors like OpenPose. So the whole entire maths of my PhD can be summarized as this. So I have this function f, which takes in these two 2D key points x and y, and it predicts z, which is the depth. But luckily, what makes this worthy of a PhD is that f is very hard to figure out, especially when you don't have any 3D data to begin with. So why am I dealing with unsupervised learning? So unsupervised learning just means that I don't have any ground truth to train with, and this is mainly because the amount of 3D datasets that exist are lacking. These are like the main three. There's human 3.6M. There's 3.6 million poses, which sounds like a lot, but there's only 11 actors and they're performing 15 actions. It's all in indoors and it's not multi-person. The second most popular is MPI-INF 3D HP dataset from the Max Planck Institute. Again, it's got 8 actions. There is outdoors, but I didn't say they're outdoors because it's in a field with one person surrounded by cameras. And it's really not generalizable to true outdoor scenes. And then the only one which you could actually generalize to outdoor scenes is the MooPots dataset, which is quite new and it's not really used that much in academia just yet. So another problem is just what's exactly going on. So the actions of the human 3.6M dataset are very varied, but because it's only one person, here is an example of someone walking. Sorry, the video's not working, but it's meant to be of them walking a dog. And what you'd actually see is them actually like trying to drag something across and then being flung around by a dog. Because in sorry, someone's listening.
Hello. Hi, you get to walk on multimodal communication. Good. Okay, you found us. It's great.
Oh, that's fine.
Okay, sorry.
So I've just introduced like my PhD. So the whole entire point of it is I'm trying to do unsupervised 3D representations of humans. So thinking about if I have this function f, which takes as input 2D key points from an image, I'm trying to predict z, which is like the depth of my person. I've just talked about why unsupervised, essentially 3D data that's available. It's very ungeneralizable to real world applications and it's very limited in its use cases. So I'd rather use like the plethora of 2D data available and actually use that to generalize to other scenes. So how can we actually acquire 2D poses? So I won't really get into like the nitty gritty about 2D detector architectures because it's quite a saturated field. But there's a top-down approach where we detect everyone in an image and then we find their key points. And then there's a bottom approach, which just means that we detect all the key points in an image and then we group them via some form of like structural information. Oh, I'm just checking something. Sorry, one tick. Oh. No, I just had an error with the image, sorry, saying the picture cannot be displayed, which is a bit of a shame. Let's check something. Oh, that's all fine. Sorry, that picture just cannot be displayed for this particular image. So I'll just share that again. So let's get it back up. Current slide. And I'm just going to make sure it's sharing the correct screen.
We're currently sharing the presenter view with the notes.
Yeah, just give me one take. Sorry, I'm just trying to get it into Zoom again.
I think you like the whole thing.
No, it's just this screen sharing. New share. Is it? Let's try to show if I make this full screen. This should hopefully pop up. And I should have. Is this one the correct one, Peter?
No. But you need to start the slideshow first and then share with Zoom, because otherwise the window doesn't exist. So PowerPoint only creates that window when the slideshow is started, and then only then you can share it.
Oh, because for us it is on. That's the weird thing.
It's on, so you have a choice of 2 screens normally at the if you now share. You should have a choice of screen 1, screen 2, and one of the 2 should be. But currently, presenter view is not running. So your slideshow is not on at the moment, according to what we are seeing here.
So
Yeah, because you're showing two of them.
Okay, now if you leave the slideshow running and you go to share screen.
I'm currently on it, actually, on my screen.
So on the share screen from Zoom, either you click stop sharing, but keep the PowerPoint running. At the moment, I think you've left the PowerPoint presenter view again.
No, if you actually see on my screen, it shows that I am
Stop share and then start sharing.
Oh, that's it. I can do it on this screen. Okay, that's fine. Screen 2. There we go. Is that working now?
Yeah, now we have the right one.
Okay,
thanks.
Sorry about that, guys. Technical issues. So which one's best? So going back to it, so top-down approaches tend to be much more accurate, but they don't work in real time. And bottom-up approaches work in real time, but they're more prone to occlusions and they struggle with small people. So now that we've kind of talked about acquiring 2D poses, let's now talk about how we can actually project 3D poses onto a 2D image. So here we have a quick setup of what's called perspective projection. This is how cameras see. It's also how we see as people. Essentially, we have this 3D pose where as Z increases, but the 2D representation of the image stays the same, we know that the 3D scale of this person must increase. So this essentially means that if you see someone who's very tall, but they're very far away, then they're going to appear smaller than if they're closer to you. And that's called perspective projection. So I'm just kind of touching a bit. So those of you who will be computer vision experts, I'm going to make a few assumptions in this to simplify it, which I'm not really going to discuss. But if you want to ask me about the assumptions afterwards, you can do. So we have this 3D pose, which is XYZ, where as Z increases, so does the scale of the person. To project the 3D pose onto the 2D image plane, we can actually simply divide the X and Y coordinates of the 3D image by Z. This is assuming that the camera is aligned with the root of the person. So obviously there's no like camera distortion and stuff like that. So we have our depth prediction, which is we give our function this model that we want to learn, the X and the Y coordinates divided by Z, and this predicts hopefully an accurate Z. And then to get our 3D pose back, we can simply multiply it by our model's depth prediction, which should give us X, Y, and Z. But what are the problems with this setup? Sadly, Z is continuous. It could realistically be anything. It can be anything from not 0, because technically you cannot be at the same location as the camera, but it can be anything from like 0.1 to infinity. And so acquiring an accurate depth prediction Z from X and Y is actually near enough. It has been I don't want to call it impossible. I think there is some mathematics which have proven it impossible, but a lot of my friends working depth estimation. So, and deep learning's moving at such a rapid field space that I don't really want to call anything impossible nowadays. But without additional information such as like another viewpoint or internal or extrinsic camera parameters, it's very difficult to actually get ground truth depth. So we use something called a weak perspective projection. So what do we mean by this? So we typically assume that the camera's at location 000 in our global coordinate that we set up. And then we center the 2D poses around a root, which we assume is the pelvis. And then we center, and we assume that when we predict the 3D, this pelvis will be at location 00C, which is a constant in our 3D space. In reality, C is just 10. We just say it's 10 units away from the camera when we reconstruct it in 3D. So what do we have in this new setup? Well, we have this 2D pose, X and Y, which we still obtain from the image plane, and we normalize our pose where C is 10. And then we do a depth offset prediction. So we don't predict the actual ground truth Z. We predict the depth offset from the root, assuming that the root is at position C. So, for example, in the original setting, you might have something like the wrist is at 520, which corresponds to 520 meters from the camera. In this new system, we'd have this wrist is at location 20, which is 20 centimeters forward from the root. And then you can calculate the depth from the camera, where the root is assumed to be at C. So you just assume that it's just a max of 1. So just 1 just constrains the prediction to be in front of the camera. And then C plus your depth prediction Z. And then you do your final 3D pose reconstruction, which is just multiplying our predictions by the coordinates. But how do we know if our 3D reconstruction is good, especially in an unsupervised manner? So unsupervised pose estimation is kind of based upon this hypothesis made by a guy called Yasunori Kudo from Japan, who said, well, let's just predict randomly, random 3D points. But if we then, and obtain a 3D estimate, well, we could rotate this and reproject it back into 2D. And if it still looked like a believable 2D pose, we could assume that the 3D reconstruction was good. And simultaneously, if we had a bad 3D skeleton estimate, rotated and reprojected this back into 2D, then the projections should not match the distribution of 2D poses. So this led to this adversarial cycle, so Yasunori Kudo introduced this adversarial cycle where he had a lifting network. I'll go onto this screen. He had a lifting network, had a random 3D transformation. This transformed 3D skeleton, went through a random 2D projection, and then this was seen by a discriminator. But you can actually improve this. So a team from out of America, led by Dylan Drover and Amazon, discovered that actually you can exploit virtual multi-view consistency. So multi-view consistency in 3D reconstruction is just if you have 2 images of the same 3D object, then the corresponding, if you have a corresponding point in 3D, you should be able to reproject that back into the 2 cameras and essentially work out where the depth is in 3D as long as you know the camera parameters. So we can send this random 2D projection back through our lifting network to get a good estimated 3D skeleton again, do the inverse 3D transformation, and then this should give us our recovered 2D pose. And this is can be compared with the input. And this is kind of how we train on supervised 3D lifting networks. It's kind of this idea of you can predict randomly, rotate it, reproject it back into 2D, discriminate against it, but also send that through the inverse transformation, and you should get the original 2D back. But what are the problems that I noticed? So the problem one was accuracy. So unsupervised approaches are less accurate than supervised approaches currently. The second was occlusion handling. So all 2D to 3D lifting models lift the entire 2D pose in one go, which assumes that the 2D detector is accurate. And in reality, this is rarely the case. So just a single missing key point will mean that these occlusion models, these lifting models just do not work. And then lastly is like multiple people. We're predicting people to be at this depth offset C, but what if we have 2 people in the scene? Well, we can't therefore have them both be existing in the same depth if both of their roots are at 0, because then they're going to overlap. So the first part of my PhD was looking at accuracy. So being a PhD student, I sit at my desk scratching my head a lot, wondering what to do. And when I was scratching my head, I realized that I moved my left arm independently of the rest of my body, which made me realize, why are we actually lifting the entire pose in one go? And actually, if you test this, you realize that long-range correlations are being induced between anatomically unassociated key points. So I tested for this. I got a load of 2D poses. I moved the left wrist a little bit to still be believable. And I found that the depth prediction, and I just analyzed the depth predictions of my model, and I found that the depth prediction that changed the most was for the right wrist. In other words, the model has learned to associate that if the left wrist moves in 2D space, the right wrist should be the most influenced key point in 3D space, which doesn't make sense when I can do this. And what you realize is that when you lift the entire pose, models become very sensitive to key points of high variance, like wrists and ankles, because deep learning is driven by variance in data. Wrists and ankles have the highest variance. These are going to drive what the rest of the pose, what the model predicts the rest of the pose. Another hypothesis was the fact that it would improve generalizability to unseen poses. So imagine that we have these two people in the training data. Well, if we just look at the entire pose in one go, we can say that the person on the left doesn't look like the unseen pose. And the person in the middle sat down doesn't look like the unseen pose. But if we actually draw the torso and the legs over, we can say that the person on the left's torso looks quite similar to the unseen pose's torso. And the person in the middle's legs looks quite similar to the unseen person's legs. So would it be better to actually have these networks which are learning independently and therefore can then mix and match from the training data to better generalize unseen poses? This led to our question of what representation to use. Should we lift the full pose, the torso and legs independently, the left and the right side, or the 5 limbs? In addition, should we split and recombine the pose or treat it as independent? So this first scenario is showing an independent network. So we have the one network which lifts the torso and one network that lifts the legs. And these simply predict the key points for the 2D that they receive. So the torso network will never see the leg key points and leg key points will never see the torso. Or should we actually learn local features and global features? So in this scenario, we used feature extractors to learn local correlations between the torso key points and local correlations between the leg key points, and then concatenated these together. And these were then seen by a full pose network, which was kind of then seeing the global pose as a whole to say, actually, the legs are more correlated together than the torso is, but in reality, some torsos do drive leg actions and some legs do drive torso actions. To put a long story short, what really surprised me in our results is that the independent networks worked substantially better than, well, not substantially better, but better than the rest. So this is an error in millimeters away from the ground truth. So for the full pose, it was 50 millimeters of error per joint. For the independent leg and torso networks, it was 41.7, and the independent left and right networks were 42.2. And here are some results where my predictions are in red and the ground truth is in blue. So it's not too bad, but clearly can be improved in some ways. This is my obligatory paper plugs. So that was the paper which was about that. So if you want to just read up about that, feel free to go off and read it. So great, now you're thinking. So now it's just time to combine my lifting model, which I just made, with any 2D key point detector. Sadly, no. We've still got the problem of occlusion. So occlusions are really prevalent in 2D lifting. A lot of papers that I read that do 2D to 3D lifting just say we just do 2D to 3D lifting because 2D in reality 2D key point detection is a saturated field. There's not a lot of research being done in it, which is a bit of a shame because deep learning's expanding at such a rate that people really need to go back and tackle these problems because real-time 2D detectors have an incredibly low retrieval rate for the full pose, even in controlled datasets such as Human 3.6M. It's so bad that if you just take open pose off the shelf and use the MPI skeleton, which is a skeleton which a lot of 3D datasets use, so it's a skeleton that you'd use if you're doing 3D lifting, you'd get the full pose in less than half of frames. It would be 45.1% of frames on average. From the front cameras, it's 55%, and from the rear cameras, it's 35%. So all these 3D lifting networks, which are touting like really good results, lifting the full pose, will work in less than half of your frames in a controlled data set. If you go outside, this is even worse. So one thing that I realized is that all our networks can work independently from what we actually saw. So the name kind of gives it away. So theoretically, you can obtain an accurate reconstruction of a partial 3D pose in an occlusion scenario. So I did the same test where I said, what's the likelihood of just a single limb being missing? And all of a sudden you go from being able to construct, to have a full 2D pose in 45.1% of frames to having a pose with a single limb missing in 88.6. I will say that this is dragged down a lot by the sitting and sitting down actions. If you remove those actions, my partial 2D pose retrieval rate goes up to about 97.3, and the full 2D pose goes up to about 64, I believe. This is just because the sitting down action, they tend to be lying down, and when they're lying down, the 2D pose is just not detected at all, and sitting down, both legs are occluded by the chair. So this led to my occlusion handling network, which is how I was invited to this talk. Peter saw me at WACV in Hawaii. Shameless plug. And this was about looking at how we can use this partial 3D pose and occlusion handling to then create a completed 3D pose. And this is where I'm going to go into the nitty-gritty bit about how to train this network and kind of how this works in general. So we have a lifting network. So the depth prediction, so it's got two paths. It's got an angle prediction path and a depth prediction path. So the depth prediction path is simply what I explained earlier. We have these two key points, X and Y, and then this predicts our Z, where the Z is the depth offset from the root. This still goes through the same thing. We calculate the depth of the camera when the root is assumed to be at C. So we get this D, which is just the max of 1 in C plus my depth prediction Z. And then we construct my final 3D pose. So what do I mean by this angle prediction? Well, if you remember earlier, I talked about this like rotation, which the poses goes through, and then it's reprojected back into 2D. So originally, the pose was randomly rotated. So in my original paper, this pose was randomly rotated between specific angles. So along the azimuth angle, it was rotated by 360, or randomly, just random anywhere. And the elevation angle was somewhere between 10 and minus 10 degrees. But the problem with this is that it leads to unnatural 2D reprojections after the rotation. And this is because our assumption of the camera is at position 0, 0, 0, and the root is at 0, 0, 0, C, which to be frank isn't true. And an example of this is shown here. So in reality, if you take a camera and you hold it up, you'll actually probably tilt it down the majority of the times. You're trying to get like a good shot of you. Because if you take a photo holding the camera up, you look thinner. So most cameras that you'll see taking photos of people are tilted down. So what you have to do is you have to accommodate for this. So a smart guy called Bastien Wendt discovered that you can actually learn the elevation angle during the lifting process. So what we do is we have the model learn an elevation angle theta, which is used to produce a 3D rotation r theta, which just rotates the pose in the direction of gravity. So this does this elevation compensation, which aligns the camera with the pose. Then you can rotate it on the azimuth angle, and then you can sample from the distribution of thetas to obtain a new virtual camera viewpoint. And this produces much better 2D poses overall in your reprojections. The next thing we looked at was actually the 2D pose discrimination. So earlier we were using an adversarial network to train to discriminate between our 2D and 2D poses and reprojections. But the problem with this is that adversarial networks collapse more than you would really want them to do. I swear there's more ways that they can collapse than there are adversarial network types. The other thing that they do is they only do what's called approximate density estimation, which means that they only learn to actually approximate the density of your 2D poses. They don't learn an actual, so it's very hard to do so we essentially want to do likelihood estimation. We have this new 2D pose and we want to estimate what's the likelihood of it coming from our 2D pose dataset. But if it's only learning an approximate density estimation of our 2D pose dataset, the likelihood will never be that good. And then lastly is training time. I'm doing unsupervised 3D pose estimation with adversarial networks, and their losses just need to balance. And I don't have any way to tell whether my model's training well or not, unless I view the poses at different time steps. And theoretically, a balancing adversarial network can train forever, and it could theoretically get better forever, and you never know if it's collapsed at any point. You just have to go in and look at it, which means it takes a very long time to train them usually. So how do we deal with this? So we use normalizing floors for pose likelihood. So put very plainly, normalizing floors are just invertible functions that map between a simple distribution. So in our case, our Gaussian, it's just a standard Gaussian with mean of 0, standard deviation of 1. and it learns these invertible transformations that map between Gaussian space and a complex distribution, which in our case is our 2D poses. So each of these functions are, in a neural network term, is defined as a coupling block. So to those of you who think this looks really disgusting, don't. It's very simple. You just have this input, which is Z. You split Z up, and you just need to remember how you split Z up. So you split Z up into two parts, ZA and ZB. ZA just gets passed through. So if you look here, ZA is just passed through. So ZA does not change. And you only do a change to ZB. We do what's called an affine transformation. This was from the real MVP paper. This just means that we just scale ZB in some way and we add a translation to it, where the scaling and the translation are determined by ZA, where we pass it through this subnetwork. So this subnetwork is just a trainable neural network. This outputs the scale and translation in the affine transformation, and then these get concatenated back together. And as you will see, this is nicely invertible because you can just split this back up. You can pass ZA back and ZA does not change. You can pass this through the subnetwork and that will still output the same S and the same T. And you can just do the inverse of this and get ZB back. So it's these nice invertible functions which you just stack on top of each other, which allow you to map between a simple and a complicated space. Another thing that's really good with normalizing flows is due to no ground truth 3D data, we want to exploit the amount of 2D data we have available. So once you have your Gaussian space, you can theoretically sample from it and pass it through your normalizing flow to attain a new 2D pose. Sadly, due to the interconnected nature of keypoints, randomly sampling will just lead to poses which look like they do not exist. So as you can clearly see here, these people are, they could work, but it's definitely not. And this is just because of the fact that learning the normalizing flow has to learn between, in your Gaussian space, you have independent variables. So you can just sample randomly through independent variables, but obviously in my 2D pose space, they're dependent on one another. The 2D location of the wrist does depend on the 2D location of the right elbow. And learning this complicated mapping is very difficult for the Gaussian flow, so it's very difficult to generate new poses. So the way that we fix this is we map real 2D poses to get a real Gaussian distribution. And then what we do is we just add a bit of noise to this and pass this back through to get our new poses. So this produces poses which are similar to the distribution in some way, and you can control this sigma function to decide how much variation they should have. So for example, if someone's got their arms crossed, if sigma's quite small and you send it back through, they should be sat down, but arms might be like slightly less crossed. If sigma's a bit larger, the arms might be like out here or something. So my lifting cycle, to scare everyone, looks something like this. But I want to just simplify that it is very similar. I have let's find the mouse again. I have a left side and a right side network, and a torso and a legs network, and these produce a full 3D pose estimate. This goes through a rotation, R1 and R2. The angles are learned by these two networks in tandem. So the torso network and the leg lifting network will learn an angle, and this is the elevation angle used to rotate this pose, and similar, this is the angle used to rotate this pose given by these two networks. These are both split and seen by their own normalized flows to do maximum likelihood estimation in the Gaussian space. I just send the pose back through to get their Gaussian variables and determine what's the likelihood of them coming from standard Gaussian. And then these are sent back through the same networks to get my full 3D pose estimate, again, inverse it, and then compare it against the input to see if it's believable. And I train my model like this. So these are my standard results. Obviously, in deep learning, you can't really publish a paper without making the big numbers bold. So I made my big numbers, well, little numbers bold in this case, because less is better error. I will happily say that the thing which I don't like about pose estimation is the metrics that we use is the mean precision from the ground truth, which is in millimeters. And in application terms, going from 4 centimeters error to 3.3 centimeters error doesn't matter that much. I'd much rather have, like, if anyone can come up with like a new way to quantify the accuracy of a 3D pose, that'd be very interesting, just because 4 centimeters or 3 centimeters of error for action recognition doesn't really matter. For stuff like rheumatoid arthritis, like I was talking about earlier, like joint mobility, it really does matter. You want it to be as precise as possible. But for like standard tasks like gesture recognition, action recognition, feature detection, animation, stuff like that, it's not really that much. Yeah. So occlusion handling training. So how do we train this? So we simply train an occlusion handling network on our partial 3D poses. So we simulate different parts of occlusion, like the left arm's missing, the right arm's missing, the left leg's missing, and the right leg's missing. And then this occlusion handling network is just trained to predict the missing joint. So if the left arm's missing, it'd be trained to predict the left arm. And the way that we do this is we say, well, this is the prediction of our lifting networks if the left arm wasn't occluded, and just try your best to match that. So these are our occlusion results, which I think are a lot more exciting to discuss about, actually. So we have a paper called Wang, which I won't talk about very much. It's by Wang et al. Sorry, and it was they randomly uniform between how it was the only other unsupervised lifting network that could handle occlusions, but to decide which points they should mask, they just randomly dropped key points between 0 and 3, which meant theoretically it could also not be occluded because 0 could have been sampled, and theoretically you could occlude the head, the left wrist, and the right elbow, which at that point the entire pose isn't visible, so it doesn't really simulate realistic occlusion scenarios, in my opinion. We trained 2 occlusion detectors, one that was trained to handle occlusions in 2D space. So this model was trained first to handle occlusions in 2D space. So we said, here's the 2D occluded pose, and here's the 2D unoccluded pose. Try and create the unoccluded 2D pose. And then we trained one in 3D space. So we trained one saying, here's a partial 3D pose, here's our unoccluded predicted 3D pose, try your best to match this. And we find that it's a lot better to handle occlusions in 3D space because the human body is more constrained in 3D space. You can more accurately determine if, for example, if my arms are like this or like this, you can, I wish I could stand up and show you actually, but if someone was in a straight line with their arms by their side, if you're viewing me from this camera, then I look like a straight line. And I could be like this, or I could be like this, or I could be like this, or I could be like this. So having the 3D information is actually a lot more beneficial when you're trying to predict it. We found that legs are a lot easier to predict than the arms, which makes sense because legs, one of them has to be on the floor at all points. It has to ground you. So if one of them's like bent in some ways or like held up, you kind of know that the other one needs to be on the ground plane. Surprisingly, we found that right arms are a lot easier to detect than left arms, which is surprising because everyone in the human 3.6M dataset is right-handed, which means that the action so it's a lot better to, what this means is that if you're driving an action with your right arm, the model learns to actually determine which arm is performing the action, and then that's actually helping it. Again, it's just because it's due to variance. If people are right-handed, they're going to do more varied actions with their right arm. This enables the model to learn better because it's learning with more varied poses. Here are some nice results of that exact scenario that I showed of my body like this. So we have someone who is essentially in 2D a straight line. We have my predictions in 3D space is in red. My predictions of the occluded limb, when I simulate the occluded scenario, is in orange. And the ground truth is in blue. So we can say that it's actually quite an accurate model, especially since it's unsupervised. What I find with the arms, if the arms are performing similar actions, the left arm prediction is very good. If the arms aren't performing similar actions, the left arm prediction is not as good. This is because, again, the right arm is kind of driving the motion. The model has learned that people are right-handed. If the right arm's performing a particular action, they tend to assume that the left arm is also doing that action. So we find, so example, you can kind of see here that the left arm prediction is as good as the right arm, because it's kind of learned to assume that, oh, the right arm's driving the action, and since the left arm's like this, the right arm should also be like this. But in the left arm scenario, it's thinking the right arm's driving the action, which means the left arm doesn't necessarily have to copy the right arm because the right arm could be driving another action. Legs tend to be quite accurate even in walking scenarios. I was very happy with it. So how would I quickly improve this approach? So I'm not currently exploiting any temporal information during the lifting or occlusion handling, which I think would improve performance greatly. And currently my approach can only handle limited forms of occlusion such as single limbs, but these are the most common forms which you'll find. You'll never find a scenario where the left arm and the right leg is missing. In that scenario, you've got a cross-body occlusion, which means the entire pose is missing. And then if only a single key point is missing, my approach currently assumes the entire limb is missing. So if the left wrist is missing, my model will assume the entire left arm is missing. So I'm kind of losing some information that way. So Peter will record this video, which he kind of showed me at Hawaii, which is what he was looking at. So 3D torso predictions for linguistics. Because of the fact that in this scenario, you only have her torso. I'll happily admit, I've been very busy, so I wasn't able to run a 2D keypoint detector on this in particular one. But I got some torsos from my dataset, and I've kind of cut off their legs and I occluded them to kind of show you what the results would be like in these scenarios. I kind of included one of someone lying down just for because I want to show that the model generalizes. There's not a lot of there's not a lot of images of people lying down, but my model can clearly see that, oh, this person's upside down with the one arm up. Obviously, it's not entirely accurate. You can kind of see that the shoulder's not correct, but the overall structure, you can definitely tell what they're doing. And again, it's like if someone's pointing their arm up, if someone's pointing their arm up, it's very good. If someone's eating, it's very good. As you can see, it's kind of got the right arm wrong in this scenario. It kind of thinks that mine's at a sharper angle, but I think that's just because the image is quite a sharp angle. And in this scenario, the left arm is just a bit too far out. But overall, I think it's very easy to see what these people are doing. So going on to the final problem, which is multiple people. So how do we estimate the depth offset of 2 or more people from a single image in real time? So this led to, I'm going to call it future work, but this is currently being presented by Hansung, my supervisor in Taiwan. So sadly, my PhD funding could only fund one trip to Hawaii, so I didn't get to go to Taiwan. So this was working with a student called Powell, where we worked on using my lifting network with a 360 camera and radars. So the radars would replace my C. So instead of having to predict depth offset, I could just use the depth from the radars. So this is the real-time videos. It's running on a 1060 laptop. The frame rate is 6, and so it's very jittery. We don't use power information, but you can kind of see that these 3 people moving, and you've got their poses being reconstructed in real time in our 3D space. So future work, which I've just written a paper and published it on arXiv, was looking at removing these radars entirely. So going back to the learning of the elevation angle, if we say that 2 people are C from the camera, so let's say we have these 2 people in a scene. Well, my model is learning the elevation angle to rotate the camera to be level with their root. So what I can do at that stage is I can actually work out their height offset. As long as they're standing on the same ground plane, it's quite accurate to work out the relative height difference between 2 people, because you can just scale them to be on the ground plane with this root offset. How accurately is actually surprisingly accurate. So this is my 3D reconstruction of 2 people with just their 2D poses alone, without any information about their height offset, any differences between them. And you can kind of see that you're able to get humans interacting quite accurately, which is something which I'm very happy with. So this is summarized today's talks. So unsupervised 2D lifting works on the assumption that a good 3D estimate will produce a believable 2D reprojection once rotated. This process does not require the full pose, and I'd encourage you not to use the full pose. You get better results via lifting of independent parts, and for linguistics especially, you typically just want the torso. And then the partial 3D pose, if you want to, can then be used for occlusion handling. So thank you very much.